My name is Sandeep Bhatia, Assistant Professor in the Department of Electronics and Communication Engineering at Rajkumar Goyal Institute of Technology, Ghaziabad. So, in a series of lectures having subject microcontroller for embedded system code KEC 061, what we have what we have discussed so far. In the previous lectures, we have seen what the microcontroller is, what are the various applications of microcontroller, what is embedded system, what are the embedded devices we used in daily life. After that, we have seen the overview of 8051 microcontroller architecture. And after that, we have started with the concept of synchronous serial communication. We have seen the difference between the serial and the parallel communication, why serial communication is used, and what are the various serial communication protocols in our subject. We have seen SPI I2C protocols among available protocols in the market. SPI means serial peripheral interface protocol, and I2C means inter-integrated circuit protocol. After that, in our next lecture, lecture 2, we have discussed I2C protocol and the advanced concept in 8051 microcontroller. Advanced concept, we have seen the updated version of the 8051 microcontroller, that is 89LP51 RD2. We have seen that. So, we have seen its architecture, we have seen the its pin diagram, pin description, and after that we have started with the one of the other advanced microcontroller, that is MCP3304 or oblique 3302. Basically, it is the family of MCP33 architectures. So, we have seen its functional block diagram. We have left with the detailed description of pin diagram we will cover in today's lecture. So, let us start. So, in today's lecture, we will start with the advanced concept in 8051 microcontroller. We will in this lecture, we will see what is MCP3304, its detailed pin description and interfacing techniques. So, these are the table of contents which we will cover in this lecture. First one is the introduction to ADC. Second one is the introduction to DAC. That is why we cover these things, because in further lecture we will discuss the ADC DAC interfacing techniques with the MCP3304. So, study of SAR successive approximation register ADC DAC with the MCP3304 we will cover in today's lecture. After that, we will discuss the detailed pin description of MCP3304. After that, we will cover the SPI interfacing with ADC DAC. After that, we will see the interfacing concepts for SPI based ADC DAC, and in the last slide we will see the various applications of this ADC DAC and MCP3304. So, let us start with the very first topic, that is introduction to ADC. You have all heard about the term ADC, that is an analog to digital converter. Basically, as the name implies, this converter convert the analog signals into a digital one. So, most of the signals, why we we will discuss why we need ADC and DAC. We will discuss in next slide. So, most signals available in the real world, just I am taking the marker. So, most signals available in the real world are analog signals. The real world signals are analog signals like temperature, sound, pressure, light, etc. These are analog signals. But in the digital world, we are dealing with the digital devices that understand only the digital language, that understand only the language of zeros and ones. So, we need to convert these analog signals that is taken from the environment into the digital one. So, this digital language is easily understandable by the digital devices. So, but as I have seen in but processors are digital devices. So, we need to convert the analog signal into the digital ones and vice versa. Why vice versa? Because for the more understanding of the things, we again need to convert these digital signals into the analog one. So, in electronics, an analog to digital converter, ADC, we can call it ADC, A/D, or we can also call it as A to D converter. It is a system that converts analog signal into a digital signals, like analog signals picked up by the microphone. Microphone converts these analog signals. That is, I am taking you a lecture, I have connected with a microphone. So what microphone is doing, microphone is picking my sound and convert into a digital signals, because it is understandable by the system. So in the same way, digital camera taking images and convert into a digital system. So ADC converts a continuous time and continuous amplitude, that is a continuous varying signal, into the discrete time and discrete amplitude digital signals. That signal is dealing with the logic 1 high and logic 0 low. So this is ADC. Now we will go further details into the ADC. One of the major, why we are using ADC converter, because by using ADC converter there is a high data acquisition rate. Data acquisition rate, we are getting the data, we are acquiring the data at faster rate by using A to D converter by as compared to other devices. So even at multiplex input. So benefit of ADC is that we can sample large data, we can collect large data and convert into a digital signal. Basically it involves sampling and quantization. There are two main concepts in ADC. First one is the sampling and second one is the quantization. I will not go into the much details of sampling and quantization. We will only discuss its definition, what is sampling and what is quantization. Basically sampling means that we are sampling the analog signal, because A to D converter converts the analog signal into a digital. So let us consider the analog signal. Let us take one analog signal that has a voltage in the vertical axis, and in the x axis it is time varying analog signals. So we need to convert these analog signals into the digital one. So we are going it for sampling. We are sampling this signal. We are sampling. We are partitioning these analog signals. So let us take partitions. We have taken some partitions here. So what we will do? We will convert this analog signal into a digital one. After that, we will go its quantization. We will decide its quantization levels. So it may have a 4-bit quantizer, it may have a 3-bit quantizer. So 3-bit quantizer have value from 000 to 1111. We can take any levels here. So in quantization, we are taking the signals and quantize it. So after quantization, we can get the signal like this. We can get the signal like this. So basically sampling and quantization are the two processes which can convert the analog signal into a digital signals. Here in this diagram you can see this is an analog signal, time varying signal, continuous time varying signal, and U1T is a continuous time varying signal, and through the sample and hold circuit here sampling and quantization done, and through which we are converting the analog signal into the digital ones, D0 to Dn-1. So this is the concept of ADC. Now let us discuss the concept of DAC. What DAC will do? DAC converts digital signal that is in the form of binary into analog signals. It is basically a inverse operation of ADC. It is basically an inverse operation of ADC. So it converts digital signals which has been converted by the analog to digital converter into a analog ones. So digital signals such as the binary signal exist in the form of bits, and it is the combination of ones and zeros. Basically digital signal we know that is the combinations of 1 and 0, that is the high and low. So we convert into these bits into an analog voltage or current. Here you can see in this diagram there is a binary input signals 0 1 1 0, and through DAC it will convert the digital stream digital bit stream of data 1s and 0 into the analog signals. This is the continuous time varying signal. Okay, this is a DAC. So why we need DAC and ADC? First of all, the information exists in real world is an analog form, as we have discussed in first slide, that the data what we are getting from the environment, it is in the basically analog form like temperature, pressure, etc. So we need to convert into a digital form. So the question is why we convert them into the digital form, and the first place we want to convert them in back. First of all, it is converted into a digital form, and again from the digital form it is converted into analog. Why we need this? Because the data we have got from the environment in the analog form, but the digital devices, digital computers which are available, they can only understand the language of digital. So, that is why we need to convert these analog signals into the digital one. But why we need to again convert into a analog form? Because for further processing, but computer cannot, but for further processing we again need to convert into an analog process, because for data acquisition, for data analyzing, we again need to convert these digital converted data into the analog forms. So, an example would be a process of audio and video editing. In audio and video editing, what we do? We convert the analog to digital and digital to analog. We are taking the images from the environment, from the scene, anything, and we convert into a digital form, and further processing we need to convert analog into the digital ones. So, this is about the ADC and the DAC converters. Now, start with the SAR ADC DAC MCP3304 oblique MCP33 advanced microcontroller. This is basically an advanced microcontroller. In the previous lecture, we have discussed the study of MCP3304. We have discussed its functional description. So, we have left with some features and a detailed print description of MCP3304. So, basically it is an enhanced version of 8051 microcontroller. So, 89 LPA51 RD2, it is an advanced version of 8051 microcontroller. So, basically it works on the two modes, either a DAC or ADC. So, this microcontroller works on both the modes. It is compatible to both the modes, that is DAC and ADC, digital to analog and analog to digital converter. We can use any of the two modes. It has a 6.5 microsecond of conversion time. The conversion time basically it takes approximately about 6.5 microsecond for the conversion from the analog to digital or digital to analog. It has a 10-bit resolution. What is meant by resolution? It is the voltage level signaling. That is the for 3-bit quantizer, it may have a 3-bit resolution as well. So, basically it has a 10-bit resolution. It has a 7 multiplexed single-ended channels or 3 differential channels. So, we have seen in our previous lecture that what are the channels, what are the differential inputs. So, it has an internal temperature sensor, it may have a LM35 etc. So, it may have an internal temperature sensor or supply voltage channels. It has a selectable voltage range from 1.0 volt plus minus to 10% internal reference voltage. So, these are the some features we have left in our previous lecture. So, let us discuss the detailed pin description of MCP3304 oblique MCP33. In the previous lecture, we have started with the pin description, but we have not go through the details. In this lecture, we will discuss this pin diagram in detail. So, what we have seen so far that in MCP3304, there are total of 16 pins. From pin number 1 to 8, these pins are dedicated for analog signals. So, we have analog input range from pin number 1 to pin number 9. So, total of 8 analog inputs available in MCP3304 pin diagram. After that, there is a digital ground in pin number 9 and analog ground in pin number 14. Both the signals share a same ground signal. After that, in pin number 10, there is allocation of chip select. It has a complement sign because it is active low signal. Oblique SH shutdown, it can work on the shutdown mode. In the previous lecture, we have seen what is shutdown mode. In pin number 11, 12, there is a serial input data and serial output data pins available at pin number 11 and 12. After that, in pin number 30, there is clock signal because to trigger this chip, we need clock pulses. So, it is supplied by the pin number 13. It is available at pin number 13, and in pin number 15 we have a V reference voltage. In the functional description of MCP3304, we have seen that analog signals are compared with the V reference voltage and the comparing output available at the output portion of the MCP3304. After that, in pin number 16 we have VDD available, that is it has a voltage range voltage range of plus 4.5 volt to 5.5 volt. Okay. So, let us discuss one by one in detail. So, in pin number 1, we can say that from pin number 1 to 7, analog inputs are available from the CH channel 0 to channel 7 input available signals. It has a voltage range of 0.3 volt to plus 0.3 volt, that is a minus to 0.3 to plus 0.3. It is compatible with these voltage range. Beyond that and before 0.3 it will not work efficiently. So, after that it has a full scale differential input range. It is defined as the absolute voltage range I in plus to I in minus. Basically, this is the differential input range. After that, this difference cannot exceed the value of V reference. We have seen that the difference that is available at the input of this MCP3304 cannot exceed the V reference minus 1 LCP or digital code. So, we have seen that from 1 to 7 analog inputs are available. After that, at pin number 8 we have a digital ground. What is digital ground? Digital ground is basically ground connection to internal digital circuitry. The system available, we have to ground it. So, it must have to ensure higher accuracy, it should have a same ground, it should share the same ground with the AGND, that is analog ground, for the efficient working of the MCP3304. So, if an analog ground plane is available, it is recommended that this device can be tied to the analog ground plane in the circuit. So, after that, in pin number further available, we have a chip select signal. Basically, it is an active low signal. Chip select is active low signal. It can be a slave select signal in SPI or I2C interface. So, basically it is active low signal. Why it is called active low signal? Because when this signal is active low from the 1 to the 0, it makes transition from 1 to 0, it works in the active low mode. So, this pin is used to initiate communication with the device when pulled low. It works only when it pulled low. So, the pin will end a conversion. What we have transferring the data, it will end when this makes transition from the low power standby mode to the high. When it takes transition from the 0 to 1, it will not work. We are not getting the output. Okay. So, after that, D in and D out available as a serial data input pin. DIN means serial data input and D out means serial data input. So, basically these pins are available to latch the data, to clock out the data. So, basically there is some important point here is that DIN works on the rising edge of the clock. What the clock signals we are providing, it works on the rising edge, and the serial output data works on the falling edge. So, at the rising edge we are going to latch the data into the MCP3304, and during the falling edge no clock signal is available, no conversion take place. Okay. So, we have seen in our previous lecture that in SPI what was the role of the D in and D out. Now, we have a serial clock. We need serial clock pulses to convert our to trigger the MCP3304 chip. We need clock signals to trigger it. So, the SPI clock pin is used to initiate a conversion as well as to clock out the each bit of the conversion as it takes place. So, we need clock pulses to execute the operation. After that, we have an analog ground. Analog ground should share the same ground pin with the digital ground for the higher accuracy. In some cases, we can use separate, but it is recommended that A ground and digital ground should share same common ground signals. Okay. So, after that, there is a reference voltage. What is the role of reference voltage? Reference voltage comparison with the analog inputs. Comparator, we have seen the functional block diagram that comparator will compare the V reference voltage with the analog inputs and convert into the and we will get the desired output. So, this pin can provide the reference voltage for the device, which can determine the maximum range of the analog input. What should be the maximum range of analog input? It will be decided by the V reference voltage. So, basically it is LSP size, its formula is LSP size. We are calculating the LSP size, and it is 2 into V reference divided by 8192. So, this is the formula through which we can calculate the LSP size. So, at the end we have a power supply VDD, power supply range from 2.7 volt to 5.5 volt. So, this is power range we have to use in our MCP3304. Now, next topic is SPI interfacing with ADC DAC. In the previous lecture, we have discussed the detailed description of SPI, serial peripheral interface. So, it can be interfaced with the analog ADC devices as well as with the DAC devices. So, here you can see that SPI has 4 pins: MISO, master in slave out, S clock, system clock, we need to trigger the system, chip select, active low signal, and slave select, and another one is the MOSI, that is the master out slave in. So what analog to digital converter do? It converts the analog input. They are getting the analog input from the environment and convert into the digital form. So basically this is the output of the slave. So basically the MISO means that slave out and master in, that is the slave are providing the input signal to the master. So analog to digital conversion take place through the slave device. So to trigger the ADC device, we need the system clock. System clock trigger these ADC devices. So how to activate the ADC pin? This pin is activated by the chip select signal. Chip select signal will trigger this device. We need active low signal chip select signal to enable this pin, ADC pin. Basically ADC and DAC both are the integrated circuits. So ADC integrated circuit will enabled by the SS or chip select pin, and the DAC chip is enabled by the input output. So here you can see there is a separate chip select line for both the ADC and DAC devices. ADC device is triggered by chip select line, and ADAC device is triggered by general purpose input output. General purpose input output, there is separate line to trigger the DAC devices. So DAC will do the data which has been converted from the analog to digital, will again convert it from digital to analog by the DAC devices. So here you can see that DAC devices, the output of the DAC devices in again in analog form. So we reconstruct the original signal. So here it means that MOSI means that master out slave in. Master out means master is providing the data to the clock, and it convert the digital pulses which has been converted by ADC into the analog form. So basically SPI used ADC TLC 2551. We have to just take an introduction of it, no need to discuss in detail. SPI based DAC available is TLV 5616 DAC. So SPI interfacing with ADC to DAC. Okay. So after that we will discuss the interfacing concepts. In our further unit 1 lecture, we will discuss the interfacing concept for SPI based ADC to DAC, that is interfacing of SPI with the ADC to DAC. So let us start with most microcontrollers. With most microcontroller SPI ports, it is required to send group of 8 bits. So we are sending the data in a group of 8 bits. We are sending the data in a group of 8 bits. Why we need group of 8 bits to send? Because to reduce the delay time, we need to send group of pulses, group of 8-bit data. So it is also required that the microcontroller SPI port be configured to clock out data on the falling edge of clock and on the latch out data in the rising edge. So basically, let us take this pulse. This is the rising edge, and this is the falling edge. At each rising edge, what we are doing? We are latching the data. And at the falling edge of the pulses, of the input signal pulses, we are clock out the data. So basically in the rising edge, there is a conversion of input to output, and at the falling edge, there is no conversion from the input to output. There is again vice versa operation, that is we are getting the data at the falling edge. So but communication with the MCP devices may be not mean multiples of 8 clock. It will be necessary to provide more than clocks are required. Why we need to provide more clock pulses? Because if for example you are converging the data from the some system, you have 8 bits of data. So for each 8 bit you need 8 clock pulses, but we are providing more clock pulses, so that if one clock pulses fail to execute, we have another clock pulses which can convert this data into the output form. So this is usually done by leading 0 before the start bit, because we have to use the concept of leading 0 before the start bit. Before the input and output conversion, we need to send leading 0 before the start bit. What is the significance of these leading 0? We will discuss in our next slide. So for example, figure on next slide show how the MCP devices can be interfaced to a microcontroller with the hardware SPI port. We will discuss with the timing diagram. So this is the timing operations of the MCP3304. In this timing operations, you can say that there are 2 modes operation, mode 00 and mode 01. Mode 11. So mode 00 and mode 01 difference is that in mode 00, system clocks convert the, here there is a concept of 00. So system clocks will trigger from the 0 to 1. When the pulse is taking a form from 0 to 1, we are latching the data. But let us take the mode 1 1. So in mode 1 1, system clocks will work like this. From there is a transition from 1 1 to 0. So let us discuss one by one. We are taking the example as in mode 0 0. We are not taking mode 1 1 because there is similar figure. There is only one difference. System clocks take transition from 1 1 to 0 in mode 1. So we need chip select signal. It is active low signal. When it is active low, we are converting the data from input to output. So at the sixth edge, there is 6 leading 0. There is 6 leading 0. So here you can see that we are transferring the data from D to D1, D0 at the rising edge. So at each rising clock, we are converting the data. We are sending the data. D in will only work in the rising edge, but at the falling edge, what we will do? You can see here that at falling edge, there is don't care condition. There D in only works at the rising edge, not the falling edge. So D out. Why D out has a high impedance state here? Because during the input signal, that is during the supply of the input data, D out work will remain in the high impedance state. There is no output when we are sending the data into the MCP3304. Here you can see that we are sending the leading 0 and you can see here that why we use a concept of leading 0, because the process for identification, to tell the processor that it is going to execute. So we have to use the leading 0 concept here to identify the processor, to tell about the processor that we are going to execute the operation from the input to the output. So here you can see that there is another bit start and here null bit and a sign bit. Why we are using it? These are the 2 extra bit along with these 2. Why we are using it? To convert our system from the input to output. So here you can see that so D out will works on the only when on the falling edge. So this is the timing operation. This is similar to the mode 1 1 operation on the MCP3304. So from these timing operations, we can analyze the operation of our SPI based ADC to DAC. So in our further lecture, we will again discuss some timer and counter operation, watchdog timer, and some more timer operation we will discuss in further lecture. So thanks for your patience, and thank you to everyone.